Cliff told me I had to make an outrageous joke about Yahoo. So you all have to tell Cliff I made a really outrageous joke about Yahoo at the start of the thing, okay? On the same page? All right. So today I'm going to be talking about scientific sustainability in scientific software, which is something that is really exercising people that are thinking about science policy and are thinking about cyber infrastructure and are thinking about advancing the way that we do science. But I'm going to start off in a slightly different place, and I'm going to start off by talking about a topic that's dear to my heart and drives the things that I tend to be interested in. And that's the question of how we can organize differently when we're working on things made out of information, and particularly things made out of digital information. All right, so we're not building cars, we're not, say, building houses, but we're building things that are made up of information. So the first thing that I'm going to sort of call an affordance is that when we build something out of information, we can have cheap reuse, right? And that is because digital information can be easily and simply copied. And I think this is incredibly well understood and drives a ton of the thinking about the way we organize around the work we do with information. So we might have high design costs. It might take a long time to write a piece of software. But once we've written it, we have really, really low instantiation costs. And I once had a reviewer object to the phrase ultra low, but I'm sticking with it, okay? They're almost zero, right? We need a computer, we need some electricity. Once we've done that, we can stamp out copies of the piece of software. We also have cheap network distribution, so we can push the code out to many, many people. All right, so what are the implications of this? Well, one of the key implications is the idea of write once and run anywhere. Share it with as many people as you like, and that leads to incredible economies of scale in production, if you want to put it in economic terms, right? We can write it cheaply and push it out there. So it's no accident that people got excited on Oprah's show when she said, everybody gets a car, right? If she'd said, everybody gets a copy of a piece of software, they'd be like, Oprah, that didn't cost you anything, right? So that's the first affordance, which is reuse. And I think that there's actually a ton of thinking about how we organize around work that's built on this idea of reuse. And so one thinks of the very high valuations of software firms are all based on the idea that once we make it, we can sell it to lots and lots of people, and we'll get really high margin from doing that. Okay. The second affordance I want to focus on a little bit more is that when we're building things out of information, we can recombine them. And that means that that's because they're really flexible, which means that we can take them and we can patch them. We can take a little bit of software code and we can make changes to it relatively easy. We can wrap them with other bits of information and make them new structures. We can extend them, we can add layers onto them, and we can also recombine them, meaning we can make them work with other pieces of information. And so that's a crucial thing for thinking about how we're going to change, how we're now going to do science in the cyber infrastructure agenda. So key to the Atkins report was the idea that through technology and software, we're going to take science up higher scales, and we're going to do it in a more collaborative fashion. And we're going to be highly innovative when we do it. Because as we know from lots of the literature in innovation studies, the ability to recombine things means that you can attack problems in new ways. Okay, so that's the second affordance of information. Yeah?
Quick question,
yeah.
Clarification. Do these affordances apply to software or to digital information writ large?
I think that's a really interesting question. At the moment, I'm trying to make them apply more broadly. I think we should come back to that at the end, because I think it might be that they might only apply to software. I'm only really going to be talking about software, so some thinking on that would be awesome. Yeah, Leno.
When you use the term affordance, are you using that in the sense of Gibson, Norman, or?
So I'm using it in the sense that there's a feature that it's flexible, which then is related to a set of practices, which is recombination. Okay, they're not recombination and flexible is not exactly the same. Whether or not it goes as far as the kind of Gibsonian, people can see that they can do it, I'm not 100% sure. So let's come back and talk about that as well. Make sense? All right. So this is key to the NSF cyber infrastructure vision, right? We're going to fund people to make pieces of software And those pieces of software are going to spread out. They're going to be combined with other pieces of software. And in doing that, we're going to have a very successful change and drive science at scale. But the thing that keeps coming up in how we're approaching doing software in science is this question of sustainability, which in short means, how do we keep this going? And so you can see here from some quotes from the NSF Software Vision document, we're going to invest, and it's going to result in robust, reliable, usable, and sustainable infrastructure. So we're going to build these artifacts. They're going to go out there, and they're going to be around for a long time. That will result in the development of sustainable software communities, sustainable frameworks, and a diverse community. But it turns out that sustainability has been a big problem. And by that, I mean that people find themselves in situations where they're funding a piece of software, it's going out into the world, might be useful for some time, but then is becoming increasingly less useful, and the projects that they funded come back and ask for more money, right? And so they're operating with this idea that software is an artifact. And once we build it, we can make many, many copies of it, and therefore it goes out and it does its work, and we've got this high economies of scale. So what I'm going to try and do is explain why we're having this big problem with sustainability in science. And to give you some idea, there's been 4 or 5 workshops funded on this and a lot of thinking within different science agencies about this problem. I'm going to try and explain it in a way that helps us know what to do about it. All right. So I'll start off with a quick sustainability framework, which really is about economic and business models that drive the production of, that sustain the production of software. So the creation of software is when we move from resources to a piece of software. We've pretty much got that bit down. Okay, you give enough chunk of money to people with the skills, and they'll produce a piece of software that does some useful work. All right. Then the idea is that software is going to be used, and in using it, it's going to deliver some value and have some scientific impact. And by having that impact, and so I would say that scientists who are building software have some of the use down, and they're increasingly seeing that the software does really change the science. It creates new opportunities to do it. But in order for a project to be sustainable, you have to have some way for that impact to turn back into resources so that the work can continue. All right, and I'll come back and talk a little bit more about the work. And so this is the crucial line here, right? Which is, how does impact, or at least use and impact, end up turning back into resources? And I'm going to quickly outline 3 really broad-based ways that we organize to be sustainable in this mode. So these are the questions of sustainability. Which are, how and to what extent does a project attract new resources? And that's a sub-question, which is, how do they turn that use and impact into new resources? And to what extent do the resources attracted suit the sort of work that needs to be done in an ongoing way? Okay? So this is sustainability through commercial sales of software, right? And so think outside the scientific space here at all. And so we make an investment, we use some resources that create software, that gets bought by people who use it in some value-producing activity, and that is their impact, and that provides money back to the project. Everyone kind of on board with that? So we've got this feedback pump by which the use of the software out there ends up directly in resources for that project to continue. Okay? Now, I didn't change the diagram very much, but now I'm going to talk about open source peer production. And I'm going to make the argument that open source works basically the same way, except that rather than bringing in dollars, what is being provided back to the project is the developer's time. All right? So we say piece of software like a BibDesk that I worked on and did participant observation on for my dissertation. Somebody else had provided resources, provided software. It helped me write my papers. And then I made some changes that helped me accomplish that better. And in doing so, I provided time back to the project, and therefore the work got done. Everyone okay with that? All right. So with grant making, which is the main mode of funding resources in science, what we have is a slightly different structure in that we get some money. Yay, we got the NSF grant, fantastic. Okay? We're going to write some software. Hopefully it's going to go out there and be used. Ideally, it will have some impact. It will drive science forward, maybe result in some new papers being published. And then after about 3 to 5 years, we're going to go back and we're going to ask for some more money. Right? And so rather than the value-producing activity over here directly resulting in resources that feed back into the project, we go through a new cycle of grant review. And if the people on that grant-making body like the impact and like the proposal for continued work, then we're going to end up with some more resources that go into play. So these are three modes in which we turn resources into software. And then the question is, how do their differences and how does the work that's being done in science affect the ability to do that? Okay. So when we think about the work that typically needs to be done in a software project, a model which I think everybody understands doesn't work, but a lot of people continue to use, is the idea that first what we do is design and we develop, and then we move into a phase that we call just maintenance, right? And maintenance is this very catch-all phrase that is used to basically mean all the work that happens after the piece of software is initially produced. And so tossed in there is everything from bug fixing to implementing new features that people want to, as we'll see, dealing with changes in the software around a piece of software. And so that category of work is really hard to wrap your head around. But we do know that if you go to a peer review panel and you promise to do maintenance, that people are not going to be very excited. And actually, in Art Chopachal's dissertation, he really talked about that. And so did work by David Rebes and Tom Finhold that was done here. Looking at how peer review panels are very focused on novelty and discovery and really are quite, don't like the word maintenance. It doesn't sound like what science funding is meant to be for. Okay. But what we're going to do is explode the maintenance category and look at the different types of work that result from the different affordances of working with information that I talked about at the start. All right. So now I'm going to talk, yeah, Carl.
Are you going to say something about how the attitude is given towards telescopes?
I'm not going to, but I'd love to talk about it because I think it's true. I think that that relates to the flexibility argument. When you build out a telescope and it's a nice solid thing, you understand why it breaks down and you understand that it needs to be maintained. I'm going to argue today that we actually don't have a strong understanding of how technology breaks down and the work that's need to be done to keep things going is hidden work and has been really hard to bring into the grant funding cycle. So yes, in a way, but I'm not going to say telescopes. All right,
So
Margaret.
I have a related
Yeah.
question, if you could just go back one slide. No, 2 slides, I'm sorry.
Yeah.
Often, the impact that's being measured, valued, and generating some additional resources is not the impact of the software. It's the impact of the science.
Absolutely.
And so I guess my question would be, how, in your view, is this model different because there's software in that loop as opposed to any science that doesn't produce any software?
Another fantastic question that
I'm not suggesting that you have to answer.
well, no, because I think that this is one of the key questions that comes out. What is the difference between software work and knowledge work? And I'm going to talk about how the affordances of the technological thing of software might make it a little bit different, but then I think the discussion is open once we get to that. So now I'm going to summarize a ton of empirical work that I have done with my collaborator Jim Herbslub at CMU and many other people too. And so I want to point out here that Paul has done a lot of work looking at how scientists actually use software and doing their science. Ewood Dielman has done much. Charlotte Lee and Matthew Beets in our community have done work on this, looking at how the software is actually put together to make the science happen. And so I'm going to summarize all that like really broadly in terms of this structure here. Okay? And the general thing is that scientists don't work with individual pieces of software. Right? They work with what has come to be known as a workflow, which is that a software package hands off data to another software package, which hands off data to another software package. And this structure may even be true outside science, but I want to keep the focus on science. So what you can see up the top here is that idea of a workflow, right? Each of those pieces of software, of course, depends on a ton of other pieces of software, right? So when you install something, often know you've got to put in place something underneath it. Most of them depend at some point on the TCP IP stack. And so each of these pieces of software has their own set of dependencies. So I want to expand the discussion of the workflow to include all of those dependencies in what I'm calling a software assemblage, which is the idea that what scientists are doing is they're taking a ton of these information artifacts and they're pulling them together in order to do work. And in doing so, interesting things happen. And one of the things here is that a component that's up here in the workflow can also end up as a dependency somewhere else. And we actually have some really interesting software archaeological evidence in the ClimateGate scandal, where a software developer was trying to reconstruct what was there before, and spent a lot of the time hunting down dependencies. And it's something that we've all been through, right? Dependency hell is usually the expression used. So it's hard to keep all this stuff managed even in kind of one instantiation of this software assemblage. So they don't just use individual packages, they use them together. Okay, so thinking about the reuse affordance of information, the idea is that we write this component once and then we send it out to a ton of users, right? And at least some users are going to have a really identical use of that piece of software. And so these are just copies out of different workflows. So here's the relatively simple idea that every time a new group picks up this component, they're going to use it in basically the same way and combine it with basically the same things. And that allows us to scale just in the same way that Microsoft scales when it sells its Office, right? And so that's a dimension of what we call ecosystem position that has to do with the number of users in total that you have. But the other interesting thing that happens is that when that piece of software goes out, people use it in different ways. And so they don't just recombine it in one way, but they recombine it in different ways. And so this original workflow over here can get extended. We get a new component added on the end with its dependencies. Another group might take the component prior. So if we're following through this component here, we can see that the ones just before it change a little bit, right? Maybe I'm going to combine it with something different. And of course, over time, the dependencies change as well. So if you start off with your camera, your visual camera, if you like, focused on the group that's making this piece of software, and you pull back, and you think about all the people that are using this piece of software, what you end up with is thinking about a very complex environment in which some people are using it in a really similar fashion, and some people are using it in a very different fashion. And that's what we call the software ecosystem, right? That's part of the ecosystem insight in software engineering, but I think it also relates to work that's been done in the study of infrastructures, that things aren't done exactly the same, they're done differently. And that's really exciting because that recombination is related to innovation, but it's also really problematic because all this stuff is changing all the time, right? And it's changing for at least two different reasons. One, it's changing because new pieces of technology kind of come in the bottom, and so new adjustments have to be made to those pieces of technology. And it's changing because of this recombination process in which these components are, one component makes a change, and then that flows out, and because that component's changed, the component next to it needs to be changed, and then that creates a second ripple. And so if you think of all these people using these pieces of software, and you think of all the work that needs to be done, you've got these kind of episodes of change. I really wish I had a video of this. I've been hoping to do an animation of it for ages. But you've got all these episodes of change that come out with ripples. And as they come out and ripple and create the need to change the surrounding pieces of software, the complements and the dependencies, that's a ton of work to do. But the other thing that happens is that the timing gets really problematic. So if one component changes and is kind of rippling out, and one person is starting to make adjustments to it, and then that component changes again, then you have to redo those adjustments, and there's a ton of kind of trying to catch up to yourself all the time. So I'm going to argue that this is a fundamental thing that happens when you have software being highly flexible that goes out there to curious and interested people and gets recombined in ways that the dependencies are multi-structured. So what we end up here is an idea of ecosystem position, which is suggesting the work that needs to be done in order to keep the software projects running. Okay? So on the vertical axis, we have the number of users, right? And on the bottom, we have the diversity of use, which really means the different components that it's arranged with. right? Component A sits between component K and I in some, and J and L in another. So as you try to get more users involved, you eventually run out of users that want to use it in the same way, right? And so in market terms, we could say, well, we got market saturation. And so we needed to tweak our product so that we could move out to a new market. And so then, once we do that, we're pushing out into diversity of use. And so you generally can't get up here, and it's very unlikely that you're going to be a successful project down here. So there's this kind of joint pushing out that as you push out to get more users, you encounter more diversity of use. And as you encounter more diversity of use, you get a ton more of these perturbations in the ecosystem, and everybody has to do a ton of work to keep that going. Because this is the work that needs to be done to keep the software project scientifically useful. Okay, so this is where the rubber hits the road on sustainability. And so we've got exogenous change from new features that people come up with and from new technologies that are there to be exploited. We've got a kind of friction of distribution. We've got work to do to support users getting started and using this stuff. But more importantly, for my presentation at least, we've got endogenous change from the complexity of the ecosystem. So changes in surrounding components prompt new episodes of wrapping and packaging and extending, which spark new changes, and we end up with overlapping chaotic ripples that make sustaining useful software very difficult. Right.
So don't APIs place a constraint on the extent and degree of these chaotic overlapping ripples? And if so, what don't they do?
So it's a great question because in industry, APIs play a crucial role in managing that complexity. And so, as I'll talk about in a minute, when Apple approaches this, they control the API very closely. And that's one of the ways in which they manage that complexity.
Right.
Okay? In open source, it's managed in a different way. And in science, it tends not to be managed very well. And that's where I'm getting to now. So I think APIs are part of the solution, but they're not a complete solution by any means. And they play out quite differently in the scientific context.
Yeah,
And that's got to do with control.
Not all APIs are closed. They're open.
Right, and if the source is available and people can fiddle with it, people will change that stuff if they need to get their science done. Sandy.
I mean, so far your point is so excellent, David. I've done this with my own open source project and a cluster of related projects. And to Margaret's question, what you just described here, the complexity where you have multiple components kind of creating this assemblage,
Mm.
and they're all developing unevenly, and so you have different version development.
Mm-hmm.
So it's those intersection points where there is a friction, and then as more people create more assemblages, you've got various states of these different components and all these different assemblages, and
Absolutely.
the chaos
Yeah.
or the need to try to
Right.
manage this chaos is where
That's where I'm focusing, right? That's the work that needs to be done to keep things sustainable. And in part, I hope I'm just saying this more clearly than we might have thought about it before. I don't think this is like hugely novel, but I think that focusing on how managing that chaos is done is key to understanding what needs to be done to make scientific software more sustainable. And that's where I'm going to get to. So, what sort of work holds a dynamic ecosystem like this together, if anything? Okay. First of all, there's sensing work. You have to know what's changing. You have to have some mechanism to get back from the edges where your components are being used to know what's changing. And that sensing work might happen at the edge. People know how their stuff is changing, but it has to be coalesced in some fashion. Okay, and then there's adjustment work. And that's changing, when a component or your environment changes, you have to change your component to keep things running. And that work might be done at the edge, and often is, by people just munging around and maybe making a new wrapper. Or it might be done at the center if the center knows that they can do it, right, at the project that creates the component. The other sort of work that needs to be done is a synchronization work, which is saying, look, if all the adjustments just keep coming out randomly, then nobody can kind of catch up, and it's really hard to cohere. And so that synchronization work, ensuring that changes in multiple components make sense together, not necessarily they're done exactly the same time, but they're done in waves so that the ecosystem can deal with that. So these are three types of work that are crucial to sustainability that are done differently in different systems. So yeah, these different types of work scale differently with these ecosystem positions, right? So if you're pushing up our number of users and diversity of use, then your new feature development and reacting to technology stuff probably scales linearly, probably scales linearly at most with that, okay? The more diversity of use you have, the more new technological environments, the more new impulses you'll get from there, okay? User support scales linearly with the number of users, right? If that's some friction to help them using things, that goes up linearly as well. It might actually be slightly less than linear because users start to help other users. And I'm sure we've all experienced this, right? So in some ways you get helped by having more users because they can help each other. The sensing work scales linearly with the diversity of use, right? If everybody's using the software in exactly the same way, then you don't need to do any complex work to know how things are being used differently. But adjustment and synchronization scale exponentially with the diversity of use. And this is really where the trouble comes in, because that's where the complexity is. So the more different places your component ends up, and the more other bits of software it ends up with, and the more those are changing, even if you assume a constant rate of change across the components, which is not even true, it's actually a varying rate of change, you end up with this work being exponential as you try to push up to the higher number of users and higher diversity of use. And that's where cyber infrastructure wants to go, right? It wants to be up there and impacting a huge amount of science, generating the support that's going to feed back into the peer review and get them more resources to keep going. Okay. So holding these things together, I hope I'm starting to convince you that holding these things together in an ecosystem is really hard work. So, but you can't unlock the potential of cyber infrastructure without it being done. And I think a lot of the literature on infrastructure has focused on how some of this work is kind of hidden and happens but is not headlined. And I'm going to be talking about how different systems that drive resources respond differently to these types of work. So basically, you've got the eco-position of software on this side, which is generating the needed work, in particular the complexity managing work. And then you've got a resource attraction system, which is bringing capable and motivated people, either by paying them, by it being open source, or by grants affording the opportunity to pay them. So that's the question. How do these different resource attraction systems cope with these questions of complexity? Okay, so markets in pure economic theory, Paul Resnick isn't here, it's such a shame, because he could help me express this one. Markets are providing insight into what's happening at the edge through the selling of software to the people. So first of all, you know that people have got it and they're using it. And in situations where you have like kind of sales engineers and marketing people, you learn about how they're using it. So in some really broad sense, market pricing signals bring that diversity back at the edges, back to the organization that's doing the production, and signals to them how they should change what they're doing. Okay. There's a little bit of hand waving in there as usual. And so they do it at the same time they generate resources. So the feedback loop for the resources actually also brings information back from the edges to know what to do. Again, this is a straight up restatement of neoclassical economics, right? But hopefully it's useful. And then those resources come in until you can fund a lot of that adjustment work internally. But when you have to drive up to diversity of use and you've got to do all this adjustment and synchronization, it's really expensive. And so I'm going to argue that generally what we're seeing here is the emergence of the platform strategy in, say, iPhones and Androids, where you suppress the complexity by disallowing a particular type of recombination. And you disallow people to recombine the work that other people have done in control. So the recombination that happens is people learning new ways to use the iOS interface. And so instead of a multi-linked, interdependent network that's generating these things, you have something that's much more structured. So I'll jump forward. So you've got all these apps that are up here, right, that then all rely on the iOS platform. And then Apple can control the speed at which it changes that platform. And so that enables them to do synchronization. And they can also get to do some sensing because these platforms all receive all the code that their users are using. And so I was up at Google recently and talking to the Android team and saying, well, how do you know what your users are doing? And they said, well, we are starting to think about doing analytics on the code that comes in so we can see how they're using our APIs and see whether people have caught up. Does that make sense? Before we release a new one. Because it's been a huge problem for Android, right? That some phones are stuck 2 versions behind and then people can't use apps, and it's huge competitive. So this is how the commercial platform providers are controlling this complexity by disallowing a certain type of recombination. But when the software is open source, you can't do that, right? You can't control how people are going to use it, and therefore you can't control that complexity. So how the hell does this work in general open source, not in science? Mark? Yeah. Sure.
Actually, one more. So that assumes kind of a perfect world. So in reality, the first part of that is completely dysfunctional. And very few companies actually know who's using the product or why. I remember walking around at some one point and the engineers just admitted they had never actually talked to a customer.
Right, and hence the emergence of the sales engineer, this like weird hybrid that's an engineer that's going to talk to the customer.
And iOS is only one type of what I'm going to call a configuration regime.
Mm-hmm.
So it's a
Very nice.
simplified mechanism,
Yep.
right, that kind of branches out at the iOS level. But there are lots of things, say, for example, Office, Microsoft Office, where they control a stovepipe, but there are APIs in, and people can build other kinds of applications off of that. But they don't change the API. They don't really care what you want.
Mm-hmm.
And so I think there are other kinds of ways of doing that. And the reason that's going to become important is because I think open source has some of those same characteristics as the more open configuration.
And I think that's true, but the general point is that there are control points at which people say, complexity is managed through this choke point, and in the commercial environment they can do that because you've got some level of control, and you can basically stop the type of activity that people are doing.
So are you suggesting that in the scientific software development arena, it's total anarchy and there are no choke points, so there's no controls?
We'll talk about it.
The mechanisms into which to get controls to help manage this complexity is the sort of science policy that we need. Episodes of where we've done it well, I really want to hear about. Okay, so in open source peer production, these jobs of managing the complexity of the recombination affordance of software are done in quite different ways than in the market environment, but they're done. Okay, so in part, the sensing out at the edge of the use that's happening happens because the end users contribute changes. And as they push those back, they're taking their adjustment work and they're making that work available to the core team. Now, they're not always going to accept it, right? Somebody says, I did this because my desk was I did this for a very specific reason, and then the developers might say, okay, well, that's not general enough, we're not putting that in, but at least they know what's happening out there. So in open source, you don't know who's got your software, but because they contribute things back, you know who's working with it in some ways. Okay, this is not a perfect process by any means, but this is how this work happens. Okay, the adjustment work is sometimes shared by the concept of pushing upstream. Okay, so as we as a project have our users telling us how they're using it, we realize that one of the dependencies needs to be changed, and a practice in open source is then to make that change and push it upstream to the dependency project, so that then you don't have to maintain it and it's maintained a little more centrally. And so these things push up this dependency hierarchy. So that's one way it happens. Finally, synchronization happens with the emergence of distributions. And I actually think that people that have studied the organization of open source software haven't focused nearly enough on distributions because they provide a crucial element to managing the complexity of recombination. And so Debian, Red Hat, and even Eclipse live in a world where people can recombine however they like. And the way they handle it is they use the choke point of distribution to synchronize out things. And so they'll, Red Hat or Debian will announce, right, we've got a new release coming out in 6 months, and that tells the community that we want to kind of coalesce in on that. And like other changes, we'll push off after it. And so that helps to manage some of the kind of intersecting ripples complexity. All right. So in grant funding, the core team has to serve its users because the whole argument for their funding is that I've made other people's science easier. Okay? So when you go back to the peer review and you say, this is all the work I did, this is all the time I saved other scientists because I've got all these users and they're doing better science, that's what people want to hear about, okay? But because the service center wants to do all the work itself, because otherwise it just looks like they're creating work for the edge. Like I can only imagine what would happen if you went back into peer review and said, yeah, we've had all of our users spend like 10% of their time adjusting and fixing our software, so we've done great, right? We might want a world that looks like that.
They're now spending roughly 50% of their time doing it, yeah.
Well, but I'm not sure that we've got great insight into that. I don't think that the science policymakers think about it that way. They probably should. So this process means that the people who have to do this sensing, adjustment, and synchronization work are not scalable, right? They're in the middle, they're funded, they try to look out there, they try to interact with the scientific user communities, but like it's quite complex, right, to learn the science. And so we know that like having the cyber infrastructuralist work with people in the field is really important because they learn that work, and so they're actually learning what's happening at the edge, but that's non-scalable. So as they try to make the argument to push up to more users, and again, Archer's dissertation talked about this as being an important element, they end up pushing out to more diversity of use, but their ability to know what's happening as they do that goes down because their methods of sensing, adjusting, and synchronizing are not scalable. So what they tend to do is the projects that are successful and sustained long-term are projects like BLAST, where their diversity of use context is relatively low and the potential number of users is relatively high, right? So if you can find that sweet spot where you can be important to a ton of science, but important in a fairly non-changing context, then you can go back and you can repeatedly make the argument that it's worth taxing science in order to pay for our software because we save people generally time. So you can make a public goods argument for your usefulness. But that only works when you can minimize the diversity of use. And so that's why you see these teams focusing on power users or like lead users, and both Archer and Charlotte Lee and Matt Beetz have talked about this. And so they end up working really closely with them so they get insight into that, but then that limits the number of users they can serve in general. So this is an inherent non-scalability of a certain way to do important work.
So you keep stressing diversity.
Mm-hmm.
And what comes to mind for me is another factor that you're not talking about is confusion of boundaries. That often your software gets recombined into other software, and you end up that the user out here is actually n steps away from the original software, not just the changes in software, it's been wrapped in other software that's integrated.
Yeah. No.
And finding the unit that is your software and how much you get as a tax. I'm imagining your taxation system. You argue 15% of that is mine. And you can't do that because
You've got no control.
so I just want to, I mean, it's not just diversity of use, it's complexity of recombination.
I'm with you. And that, yeah, it's really the set of complements and wrapping that happens. So yes.
And I would add one other thing, which is that I think you're confusing, in terms of scalability, the power user, which is a very small number of very good users,
Mm-hmm.
with what is essentially a long tail problem that you're not conceptualizing here anyway as a long tail problem.
It is a type of long tail problem, yeah.
It's a
Yeah.
totally long tail
Uh-huh.
problem, and we'll talk later because
Okay.
this is what Seed is trying to address.
Okay, good.
But, you know, this explains to me a lot of why the funding for scalable, sustainable scientific software ends up supporting not the long tail, but a very small number of pretty similar
Mhm.
high power users. So, yeah.
Yes.
So the high
Oh,
number
oh,
of
I'm sorry.
users.
Just follow up here?
Yeah, I just wanted to follow on that. So the point about the power users is not just that there's a small number who are good at it, but that they talk to the developers all the time.
Sure.
It's that thick, deep interaction.
This isn't working, we need a new feature. So
Right, whereas in the long tail,
exactly.
the power user is the developer. I mean, this is the point. You've got a very, in a project that has, say, 5 people, what happens is it's not funded for a person to be the developer and a person to be the power user of what that person is developing. It's a graduate student who kind of takes to it
Mm-hmm.
and then becomes both the power user and the developer.
Exactly where I'm going.
So, one
Yeah.
issue that you may get to is that this is, on one scale, this particular problem you have is an advantage being funded. Because basically, I used to work on analysis and design, the cost to maintain software is not insignificant, it's pretty significant.
Yeah.
And so if you put that up front, if someone as a founder, it becomes a bigger hurdle to overcome. And I mean, are you afraid or concerned that a lot of these projects just won't get funded anymore? When people realize their true cost in the long run?
We are currently doing our cyber infrastructure funding as though this problem wasn't massive. And when I get to my science policy implications, we will focus on ways that we might be able to fund types of research that will help reduce this complexity other than pouring more money at it. Okay, because I am concerned. I'm very concerned. So are they. Small coda here. The problem of not getting inputs from the edge is really strongly made worse by academic reputation. And in 2013 at CSCW, Jim Herbslop and I published this paper. This looks at all the external contributions to NCBI BLAST. All the ones up here, fork and return, and they had multiple different types of incentives. Fun, complementary goods, on the ones down here that forked and didn't return were all fun, all motivated by academic reputation. These people published papers, and they did not, this is all based on interview data, they did not want to push it back into the core because that would then undermine their ability to have something for reputation. And there's lots of interesting stuff to discuss there. I'll come back and give that talk if you like. But this makes it all much worse, because if you can't get contributions in from the edge, then you've got to go out to the edge and say, what are you guys doing, right? Okay. So what we start to hear is that scientific software developers go to workshops and they say, look, this is really easy. The NSF should just tell people not to change stuff, right? Just enforce it. Because one way you can manage complexity is command and control. And part of them hates that they're saying that because they know it's anathema to the way science works. But it's also anathema to the fact of open software. You can't stop people fiddling, right? People are going to fiddle with it. Not fiddle, I said tinker. Tinker's a better word. And digital flexibility inhibits your ability to do that command and control. So not only is it countercultural, but you can't do it. So it's a crap way to try and manage this complexity. So to summarize where we are, grant making doesn't have good built-in feedback mechanisms that facilitate the sensing, adjustment, and synchronization work. Other production processes, resource attraction systems have a better way of doing that. Currently, the cyber infrastructure discourse invokes both reuse and recombination, but we fund as though the only affordance that was there is reuse, right? Because we don't manage this complexity. Okay, what policy responses can you do? One, you can try to transition the resource attraction system. You can say, right, the grant's just to get you going, but then you've got to move into a different one. And then the second one is that we can change our grant, the way we make grants. Okay, from going from a grant funding to a commercial resource attraction system is something that people talk about all the time. And it does happen. It does work. If you can find that sweet spot in which your market size is big enough that the work that needs to be done can be pushed in. But remember, whenever you go out to bigger markets, you get more diversity of use, and so you're pushed off on this angle. And in science, that's really problematic because they're generally small enough to begin with. And so to make them big enough to fund the work, you get pushed up there and it's very complex. Doesn't happen so much in general software because there's more people. But this whole idea of transitioning from an academic transitioning from a grant to a commercial project is hugely difficult, right? You've got to move, now you've got to manage a business. You've got to have users who have a budget they can spend on it. And a lot of grants, you're not allowed to spend money on the software. Then you've got to convince the funding agency that they're not paying many times over, right? Because they start to think, oh, I'm just buying the same piece of software 10, 15 times, not I'm collectively funding the maintenance work, which is what they probably should be thinking. And another problem is that once you go commercial, you are forced to go and seek out customers with money. And there's a great example of a physics database that went commercial, and the scientists were like, they won't listen to us anymore, they won't do anything for us, because it turns out that database was particularly useful for Wall Street traders who, you might be surprised to hear, have a lot of money and command the attention of the core team. And so this happens over and over again. It's a big problem. Transitioning from a project to an open community, and I wish I had an hour to talk about how hard this is. Okay? You're going from a situation where a PI with hierarchical control over his or her grad students and managing with money if they're employing software developers now has to turn around and manage with this sort of suggestive stewardship and encouragement that is part of an open source community. Yet PIs don't do that, right? That's not part of the whole principle bit. So you've got to do a ton of things. You've got to maybe change your architecture from a monolithic architecture that works if you've got an internal team. You've got your collaboration infrastructure has to be opened up. That's actually the easiest part, and it's not even easy. You've got to change your governance. You've got to move from we make the decisions to I'm going to let my competitor in another lab decide what code goes into my bit of software. And yes, you've got to move from managing FTEs to doing that. And just because you move a project to an open peer production community doesn't mean that distributions naturally emerge to manage the complexity and synchronization. So this is really hard. Doesn't happen nearly as often as people wish it did, but it is the preferred solution at the moment. And I'm trying to make the argument in these circles that it's much harder than you think, and it might not even be what you want to do. Okay, the second option is to make different types of grants. And so if I'm right in diagnosing that sensing, adjusting, and synchronization work is key to managing the complexity, then can we use grants and our academic horsepower to attack this problem in new ways? So first of all, we could fund, but also more importantly, develop reputational rewards to doing this sort of work. So for example, sensing. It's measuring the diversity of use context. It's actually a really hard problem, but it might be amenable to systematic interventions. And so for example, the Texas Advanced Computing Center now has a way of looking at the jobs that happen on its supercomputers and seeing what in a limited area of software, seeing what software is running in it. So it's starting to see the edge a bit better. Some of the hosted systems, like Galaxy, actually have all the workflows that people are doing. And so by automatically analyzing those, they can see what's happening with the diversity of use and scale some of that sensing work. Now, this is, you have to overcome real, genuine concerns about scientific competition. For example, it makes sense to just say, hey, everyone should send all their code that's running to a central group that can analyze it. And then the structural biologists say, I'm never doing that, because if they find out what molecule I'm working on, I'm sunk, okay? Because the space is like really sparse, and even knowing what molecule somebody's working on is like too much for scientific competition. So that's a huge barrier to doing this, but it's a problem that's probably amenable, and if we can get our machine learning type people involved in this, we can do new sorts of work in the software ecosystem. So we should be funding grants like that. We want to do adjustment, and we want to actually have that adjustment happening best at the edge, and so incentivize projects to come back to the grant and say, look, out on the edge, we've got lots of people contributing code. Not, we saved scientists a ton of money by the work we did here, but we're good stewards, and we brought that code in, and we helped with them. And that's just a change in argumentation, which could easily be pushed out. But you do need to overcome that reputation problem I just talked about not wanting, outsiders don't want to contribute their changes back. So that might involve a set of things about not writing a paper with solid authorship that you ask people to cite. Because if you want contributions in the future, having asked people to cite that solid paper which doesn't change means that they can't get access to the reputational rewards of other people using that software. So an interesting problem for scholarly communications people to perhaps focus on. So finally, we could also fund, and we should fund, more distribution work and innovation in distribution work. So for example, one opportunity would be in having simulation models of the software ecosystem and knowing what happens when you change a component over here. How quickly does it flow through this network of dependencies? And so which ones might we want to slow down at different times and maybe not fund for a while because things might flow out. So this is some ideas how we can change the way we make grants to build in opportunities to do the sensing, adjustment, and synchronization. All right. And this pretty much summarizes the whole story. The affordance of reuse is really important. Recombination is the other affordance. Recombination results in extreme flexibility, which then results in an ecosystem and immense complexity. And if you don't fund or otherwise incentivize the work to manage that complexity, then you end up with the scientific software sustainability problem. I'm done.